Okay, good. So that means that we should probably just wait another couple of minutes for people to filter in, and then we can begin.
So David, I heard you're in Amsterdam now.
Yeah, we're enjoying it very much.
You're there for the whole year, or?
Yeah, for the whole year because of the school
Great.
of my son. But my wife
Yeah.
and my son are enjoying it so much that they want to stay. So this is
Oh, that's
this
good.
is a work in progress.
Great.
Awesome.
No, we're good. We're
All
having
right,
fun.
so maybe we should get started. So it's already a minute after 10.
I thought you
Right.
should make your V smaller because otherwise it looks like University of Virginia. No, but
Oh, okay. I guess that is a possibility. Universiteit van Amsterdam. UvA. Okay,
Oh, very good.
that should do it.
All right. Not that there's anything wrong with the other UVA, but
right.
No.
just to break the degeneracy. Yes.
I got confused. I thought you were in Virginia. Seriously,
No, I'm in
it's not
Amsterdam.
like.
Very good. All right. Well, maybe we can get started. So today we're delighted to have David Berenstein join us, and he'll tell us about his recent, very exciting work on staggered bosons. Go ahead, please.
Thank you, Alexei. Okay, so so this is based on two papers. The first one I wrote kind of in March, or finished writing it in March, and then the second one I just released with one of my students, Thomas Lloyd, very recently. And then Staggered Bosons is a title for a new construction, well, novel. I don't know how to say it. It'll turn out to be more familiar once we see the example. But the name was suggested to me by people who do lattice because the construction is very similar to staggered fermions. So the idea of staggered bosons is very similar to staggered fermions. And let me tell you where this started from. So I've been thinking about Hamiltonian physics, and the reason is that this is how quantum computers work. And I have, been researching a little bit about how to put field theories on quantum computers. And you can ask, so the goal is to find interesting field theories. And then because it's quantum computers, we eventually want to have finite number of states per unit volume on a lattice that can eventually be simulated. But today we're going to talk about bosons, and bosons have, in principle, infinite occupation number. So I'll tell you how to go from bosons to these more quantum gadgets along the way. So I've been thinking about that, and then a question is, we've been doing a lot of Lagrangian physics, at least in string theory lately. And then there's a question whether there's something more Hamiltonian in nature that would not be immediately available in naive path integral methods. And as I said, this is related to quantum computing, where we simulate Hamiltonians and non-Lagrangians. Basically, the question is, if you have both x and p in real time, there's not usually a guarantee that you can weak rotate it to the Euclidean signature. So this is really about whether there's something about real time that cannot be done in Euclidean time. And there can be some intrinsically Hamiltonian systems that should be analyzed without integrating out the p's. And this is what this is really about. The overview is, I'm going to try to look for interesting lattice realizations of gapless field theories. So the word interesting here means gapless. And then I'm going to try to find the minimum number of variables. And then I want to tell you that there's some symmetry protection that's not available in conventional theories. And it turns out that this thing that I thought was very different is actually the non-invertible symmetries that have been recently studied a lot. And then the one example I'll spend a lot of time is talking about half bosons in one dimension, and then I'm going to speak about some generalizations. So this is kind of the overarching goal, and then the details are, I'll talk about the chiral boson as a model of a half boson and tell you that that was the inspiration for a lot of this stuff. And then I'll tell you how to put it on a lattice, or rather how to get a close analog of it on a lattice. And then we'll talk a little bit about, topology, which really means zero modes. And then we're going to talk a little bit about what's the difference between a symmetry and an algebra automorphism, because this seems to be at the heart of what non-invertible symmetries are. There's an algebra that you have around, there's an automorphism of it, and then the question is whether that is realized as a symmetry in the Hilbert space or not. And the difference between these two things is where non-invertible symmetries kind of lie. So I'll talk a little bit about what are non-invertible symmetries, and then I'll talk about, how to get these half bosons from regular bosons. And then I'll talk a little about the compactification of these bosons, which is, the goal is to basically go to this finite number of states per unit volume. And then once I describe these clock model spin chains, which have been around since the 80s, I'll talk a little bit about Kramers-Vanier duality, and that in this realization, it's the same thing as T-duality. And then the non-invertible symmetry is both Kramers-Vanier duality and T-duality. And then I'll go into some generalizations to higher dimensions, fractons, and then supersymmetry if there's time. And then that's the plan for the talk. Okay, so let's start with a half boson. So let's start with a chiral boson in one dimension. It's half a boson because you only have half as many harmonic oscillators as a regular boson. There's only left moving degrees of freedom. And then if you look at this is a proper field theory, but it does not give rise to a modular invariant partition function. So sometimes we would discard it in Euclidean field theories because it's kind of a little bit pathological in Euclidean dynamics. But it's a proper field theory. It's what people use in the quantum Hall effect all the time. And the full boson has both a left mover and a right mover. So the idea is that this is half of the degrees of freedom of a regular boson.
Is it a compact boson?
No, this is just, at this level, we're just doing oscillators. We'll talk about zero modes later. So
Okay.
just count oscillators and zero modes later. Okay?
Okay.
Okay. So there is actually a Hamiltonian formulation. And that is where you quantize this classical equation motion by having non-trivial Poisson brackets of the phi's, which involve a derivative of the delta function. And then what's important about this Hamiltonian formulation is that the Poisson bracket does not have any phi dot in there. So this Poisson bracket is antisymmetric, the delta function is symmetric, the derivative makes it antisymmetric, and it's a constant function essentially, or it's a constant matrix. So it defines a proper Poisson bracket. And the Hamiltonian that you can write, which includes the speed of light, is an integral of phi squared over 2. Okay, so you look at this system, and if all you're given is the phi's, there's no relevant deformation that gaps the system. It is relativistic. It has a UV with a non-trivial 't Hooft anomaly. So the infrared needs to be gapless also. That would be the way we do it. The point is that if you use this Hamiltonian, this is actually the minimal quadratic form of phi that you can have. There's nothing that's lower degree in phi that does anything interesting. If you add a linear term, for example, you can just do a field redefinition of phi and shift it by a constant, and you get the same Hamiltonian. So there's no way to gap it. Okay. So this is the starting point. And let me tell you what this Poisson bracket is. You might recognize it. This is you turn Poisson brackets into commutators, this is just the CQ1 chiral current algebra in position space. So the derivative of the delta function is the Schwinger term that classifies the anomaly. So if you look at this equation and you remember now that the phi's are j's, then the derivative of the delta function is the anomaly of the U1 current. Okay. So the statement is that you can use the anomaly in some sense as the Poisson bracket, and then you can build a theory with just the left U1 current algebra. Now I'm just going to take this theory and turn it into a lattice. So I want to do the same, but in a lattice theory. So if I try to do the same, the anomaly matching of 2D gravitational anomaly prevents me from doing a theory of just a left mover, because in the UV, I have that the left central charge and the right central charge vanishes, mostly because when you're on a lattice, there's no infinitely far away UV. So the theory starts anomaly free in the UV. So in the infrared, it needs to be anomaly free also from the point of view of the 2D gravitational anomaly, if it's relativistic or approximately relativistic. So anomaly matching will tell you that you cannot get a purely left boson. So you're going to have some right movers also.
Sorry, can I ask a question about that?
Yes.
So are you, I'm a little bit confused. So this anomaly here is an 't Hooft anomaly.
Yes.
Certainly in some cases, there are lattice models that can reproduce a 't Hooft anomalies at finite lattice spacing.
Yes.
So what is special here that you cannot imagine having in a
No, the idea is that in the far UV, meaning at distances that are smaller than the lattice scale, there's no degrees of freedom. So if you're very naive, you would say that the difference of anomalies needs to be 0. And the anomaly matching would tell you that in the infrared, you need to have a theory which is anomaly free. Okay.
Would this apply to any 't Hooft anomaly?
No, there's some discrete 't Hooft anomalies where this doesn't apply. What I'm going to tell you is what really happens.
Okay, please go on.
So again, this is a statement about if I'm just counting degrees of freedom in the gravitational anomaly, in the deep UV, there's no degrees of freedom at sublattice scales. So the real question is not whether the 't Hooft anomaly vanishes. This is a kind of red herring. The real question is whether you get a gapless theory or a gap theory in the infrared. So if you're going to get a gapless theory, you might still get that there's left movers and right movers, but there might be some interesting thing that kind of compensates for the fact that the naive UV anomaly vanishes. Okay, so what I'm going to do is I'm going to take the idea of a half boson seriously. So instead of having X and P's at each lattice height, this is kind of the usual way I would build a boson. I'm just going to have one bosonic variable per lattice height. And I still want a non-trivial Poisson bracket. So if you have a bosonic variable, the Poisson bracket with itself must vanish. So the only way to get something non-trivial is to talk to the neighbors. So if I want to do something approximately local, the simplest model I can write down is that the Poisson bracket talks to the neighbors and it needs to be an antisymmetric matrix. And the closest analog I could find was a discrete derivative of the delta function. So you basically say that the Poisson bracket of the ith and the jth variable is basically 1 to the left and -1 to the right, or however you want to call it. Okay. So I have to make a sign choice. I could have chosen minus plus. It doesn't matter in the end, but I have to make a sign choice at the beginning. And then I'm going to call this particular sign choice that I made here the plus minus, as opposed to minus plus, the left moving one. Okay. And then let's go from it. So I'm just going to try to copy paste what I had before. So I had a Poisson bracket, which was a derivative of the delta function. Now I have a discrete derivative, the closest analog on a lattice. And I'm just going to take the same Hamiltonian I had before. So this is kind of like a discrete derivative of the delta function. And as I said, I make this sign choice. And then the Poisson bracket now that I built is an antisymmetric matrix. It's constant and therefore defines a phase space. Okay. So the Hamiltonian is just 1/2 of Q squared. So I'm doing the same thing I had with the current algebra. And if I take the equations of motion by computing the Poisson bracket of Qi with H, I get something that looks like a discrete derivative. And then if I'm being naive, I would say that Q dot is twice the derivative with respect to X of Q. And then that would reproduce my first order differential equation for the left mover, okay? So the point is that if I'm very naive, I would say I have succeeded and that, you know, I've gotten away with doing a Hamiltonian for the chiral boson. But that's not the full story. The full story is translation invariant. You have to do a Fourier analysis in position space. And then what you find is that, yes, you have a first order differential equation, but what that means is that you have a dispersion relation that depends on quasi-momentum k because you're on a lattice, and then you get -2 sine of k. So the proper notion of low energy is frequency equal to 0, not k equal to 0. So when I was doing this approximation that Q dot is 2 derivative of X of Q, I was implicitly assuming that I had a very slowly varying field, and that might not be a good approximation in the infrared. So what you find is that sine of k has 2 zeros on the Breuilian zone, one at 0 and one at pi. This is the same argument you would have for fermions. When you have fermions, you have a first order differential equation. In this case, omega is single valued, but if you cross 0 at one point, you need to cross it back if there's a continuous dispersion relation. And this is the usual problem of doublers with fermions. So when you have fermions, you have doublers, and this is a statement that the left mover and the right mover are at different points in k-space, but there's 2 degrees of freedom, one left mover and one right mover. And then it's straightforward to quantize. What's a raising and lowering operator depends on the sign of omega k, and the mode at k ends up being conjugate to the mode at -k, just like regular boson. So really importantly, there's 2 things that happen. First is that there's only one mode per k, not one left moving and one right moving per k. There's only one mode per k. And then the mode at k is, let's say, the raising operator, and then the mode at -k is the lowering operator. Whereas in a regular lattice, you would have a mode at k, which is raising operator, and another mode at k, which is a lowering operator, if you had both x and p's at a point. Okay. So what's the infrared? The infrared is omega k equal to 0. There's 2 zeros crossings. One of them is the left moving, where all the spins are aligned. All the bosons are very slowly moving relative to each other. And then the right movers are at k equal to pi, which is basically what we will call an antiferromagnetic or Neal-ordered condensed matter, which is basically where things go maximally difference in sign. And the important issue is that omega of k is a single valued function of k. So if you add perturbations or deformations, you don't alter the fact that there's crossings of 0. And because the mode at k and -k are conjugate to each other, the mode at 0 and pi are actually self-conjugate. And what that means is that they're not really oscillators. They're central elements. Because there's no raising and lowering operator that has this kind of property that a single mode is conjugate to itself in Hamiltonian classical physics. Okay, so if you go to the Neal-ordered degrees of freedom, the ones that are maximally varying, it turns the sign of the left moving boson into the right moving half boson, and it changes all the signs in the Poisson bracket, and that's because you're doing it in an alternating form. So the point is that there's no real distinction between the left moving choice and the right moving choice. I just have to make one at the beginning. And then the right mover is in there. It's just that the choice or the difference between the left mover and the right moving choice is who's at 0 momentum, it's the left mover, and who's at pi, which in this case was the right mover. And if I switch the -1 to the j, I would swap the notion of where the left mover 0 mode and the right mover 0 modes are. Okay. So there's some symmetry protection. A left and a right mover cannot mix if you keep translation invariance because there are different values of k. One is at k equal to 0, the other one is at k equal to pi. So you cannot mix a mode at k equal to 0 with one at k equal to pi and preserve momentum. So basically, this massless boson is protected even in the presence of interactions. Okay, that's interesting. In this case, it's a critical theory. It's a left mover and a right mover. So if you go to a big lattice, the momentum is quantized in units of 1 over L. And then if you rescale the energies to be compatible with the lattice side, then for each low moving momentum n, you have an oscillator of frequency n, and that's for the left movers. And you can do something similar with k close to pi, where you take k approximately to pi plus some other piece over here. And that's only one positive frequency mode per n, your k equal to 0. And you can do the same, as I said. So you can split the left movers and the right movers, and you can find that each of them kind of has their own low energy in k. Yes?
Is there an analog of a Wilson term that you could add to split?
No, not yet. And part of it is that there's 0 modes. But I'll show you something else that's kind of fun. Okay?
Okay.
So if you go to an infinite line, there's 2 0 modes. One of them is kind of the left moving 0 mode, the other one is the right moving 0 mode. Or you can split them into, one of them is the sum of the even lattice sides. You can check that this is a central element because it commutes with all the neighbors, +1 to the right, -1 to the left. And then the C even is something that commutes with all the Qs. And the C odd also commutes with all the Qs. So there's 2 central elements in the algebra. So the idea is that when you look at the Qs, once you split them in oscillators, there's raising and lowering operators plus these 2 central elements. And then you can ask, do they survive if I do a finite periodic lattice? And now there's a distinction on whether I have an even number of sides or an odd number of sides on the lattice. So if I have an even number of sides, the number of bosonic variables is even. There's going to be an even number of 0 modes. It can be 2 or 0, depending on if the lattice is periodic or antiperiodic. And when you have an odd lattice side, there's 1 0 mode. Okay? And the reason is that on a lattice with an even number of lattice sides, you can still split between even and odd. In a lattice with an odd number of lattice sides, once you get to the end and you come back, what was even becomes odd, and what was odd becomes even, so there's only 1 0 mode. There's another way to explain this. You can look at what's really going on, and then when the circle is kind of the quasi-momentum, here I have the 0 line, and then as you move on k along the circle, there can be 2 crossings of 0, or 0 crossings of, or 0 elements at 0 on a finite lattice side. And what you see is that these red dots are what you get when you have anti-periodic boundary conditions, and the blue dots are what you get when you have periodic boundary conditions, meaning there's an even number of 0 modes, so one for the sum of the Q odd and another one for the sum of the Q even. And when you do anti-periodic, then they get twisted, and the symplectic form that you get becomes non-degenerate. And what you see is that these 2 choices are parity invariant, and parity here is reflection about the vertical axis. When I do this now for odd number of lattice sides, I get that I need to have an odd number of these blue dots. And if I have a 0 mode for the even lattice sides, sorry, for the sum of the Qs, then and I place the rest of the blue dots on the circle, I find that first of all, the states are not parity invariant, meaning that the spectrum of the left movers and the spectrum of the right movers becomes different. And moreover, so that parity is broken. But here you have, let's say, a 0 mode for the left movers, and for the right movers, there's no 0 mode. And the notion of the mode n is a half integer. So what you have is that the left movers are kind of like periodic, and the right movers are antiperiodic. And the reason for this, from the point of view of just the Poisson bracket, is that a non-degenerate Poisson bracket requires an even number of variables. So if you have an odd number of variables, no matter what you do, you'll always get exactly one zero mode or an odd number of zero modes. Okay. And if you do an open interval, if you have an odd number of sites, the same reasoning applies. There has to be one central element because the Poisson bracket is degenerate, because a non-degenerate Poisson bracket requires an even number of variables. And if you have an even number of sites, you get no zero modes. So one zero mode is like Neumann boundary conditions, and no zero modes is like Dirichlet-Neumann. Now, let me tell you what this counting is. It's very similar to counting of zero modes for Majorana fermions. So when Kitaev did his Majorana fermions on a wire, the counting of zero modes depended on whether the number of sites was even or odd. And the reason why the counting is the same is that when you give a mass to Majorana fermion, you need to pair them in groups of two. The Majorana mass matrix is antisymmetric, and therefore the statements about even versus oddness of numbers of zero modes apply to the Majorana fermions just like they do to these half bosons. So these half bosons are similar to Majorana fermions on lattice, and Majorana fermions are one way to think about staggered fermions, in that half of the degrees of freedom are on one side and half of them are on the next one. So the name staggered bosons is the statement that, you know, half of the degrees of freedom of a boson are kind of split between neighbors in some sense. Okay. So let's talk now about translation.
Sorry, just
Yes.
probably a very dumb question. What's the total dimension of your Hilbert space here?
Still is infinite. I have
Infinite, right?
oscillators. I haven't fixed that yet. I'll fix it in a bit.
Because for Majorana fermions, of course, it's not infinite, right?
Right. So that is the issue with these gadgets, that I cannot put them on a quantum computer yet. But I'll fix that in a little bit.
Okay.
Okay. So let's talk about translational symmetry, which is the real question is the translation of Qj to Qj plus 1 a symmetry? I've been acting all along as if it is. I've been doing Fourier modes, and I've been trying to figure out, you know, what happens. And then the problem is at the level of zero modes. The idea is that when you have the Qj going to Qj plus 1, you turn the zero mode of the even sides into the one of the odd sides and vice versa. So when you go from even to odd and odd to even, you're swapping the two zero modes. So as an algebraic statement, the symmetry of Qj going to Qj plus 1 is a symmetry in the sense that it is an automorphism of the algebra of the Qs, but it's an outer automorphism. For the oscillator piece of Q, the Stone von Neumann theorem guarantees that when you have these two algebras that are shifted by 1, the oscillator pieces can be converted into an actual unitary on the Hilbert space for the representation theorem of the oscillator. That's the Stone von Neumann theorem, that there's only one Raising-Loring operator algebra that you can write. So anytime I talk about a symmetry of the operators in this case, for the oscillators, I can immediately upgrade it to a unitary on the Hilbert space of states. However, this is not necessarily true for the central elements, because there's no Stone von Neumann theorem. So central elements that commute with everything in the Hilbert space become C numbers on an irreducible representation. But then the question is, which allowed values of C odd and C even you're going to get? And now, Igor, this is when it gets to the issue of whether the boson is compact or not. So the idea is that when you swap C odd and C even, it almost works, except that the label C odd and C even swap, and even though one representation might be allowed, the other one might be disallowed in the Hilbert space. So the whole issue of whether this is a symmetry or not depends on just the zero modes. The rest kind of goes along for the ride and doesn't care. It's just the zero modes. So you can concentrate everything on the zero modes, and that's where all the problems lie. Okay, everybody with me? Okay. So at the level of zero modes, we have no guarantee that it's a symmetry.
Just one comment. So at the level of Majorana fermions, this unit translation is like a discrete chiral symmetry.
Yes,
Right,
and the same is true here.
But I see. So you say it's same is true here?
Yes.
Mm-hmm.
I'll show you later what this really is, but it is exactly of that type.
Because for Majoranas, you just, in fact, we just wrote a paper on this with Silvio, Ross, Benjamin. Like you put the upper component on even sides, right, and lower component on odd sides.
Right.
So it's just interchanges basically upper and lower components. So.
Right.
But
so
here,
the same...
your bosons are not doublets in any sense, are they?
No. I'll show you a different version of what this is. And when I show you that, you'll understand what this really is. At this level, this is an algebraic statement. And as I said, I was stumbling into these things by looking at the algebra. And then the question is, how do I understand this in some other variables that makes it clear what this is? Okay, it will turn out that this is T-duality. Okay.
Interesting.
So here's the important thing. As I said, at the level of zero modes, there's no guarantee that it's a symmetry. But if you do it twice, so if you translate twice to the right, then the central elements go back to themselves, and now Sturm von Neumann fully applies, and therefore all of those are symmetries. So translation by twice is a symmetry in the traditional sense of Wigner, that you can write a unitary that realizes it, and acting by once doesn't. So the operation of acting twice is like a translation symmetry on a conventional system. And then the question is, when I swap the zero modes, the even and the odd, can I get away with anything? Well, I can make it a symmetry on the subsector representations where the pairs of C odds even can be matched across the aisle. So when I have pairs of C odds even, and I have the dual pair C even C odd with the opposite order, and both of them are for some reason in my Hilbert space, I'm allowed to build a symmetry on those subsectors of representations where the labels can be matched. So the idea is, what do? You do the best you can do, which is basically we just do a projection on the shared subspace of matched pairs of zero modes, and then the symmetry that I had before that translates by one acts only on this subspace of the Hilbert space where the zero modes are matched, and still commutes with the Hamiltonian. And everywhere else, I extend by zero and say, basically, I don't have a candidate for what the symmetry would do. So the idea of this symmetry is that it's a symmetry that has a projector, and the projector is basically the thing that's at the heart of being a non-invertible symmetry. And what you'll see in many places is that, some symmetry squared is going to be some true translation in some more traditional sense times a projector. The projector is the thing that makes it non-invertible. And I'm calling this
Kramers-Wanier duality, also known as T-duality. Isn't it like the simplest example of non-invertibles?
Yep. And we'll see how it shows up in some examples. So here I'll show you that what I just did is T-duality, and I'll tell you what this projector does.
Yeah, I think.
So I need to show you why this is T-duality. I just showed you some abstract isomorphism of an algebra. So again, this is at the heart of what a non-invertible symmetry is that there's some projector sticking around. Now, if I go to the continuum limit, translation becomes kind of trivial, translation by one on the lattice or by two in the lattice, in the sense that the quasi-momentum of everything has gone essentially to 0 or to pi, and translation by 2 is basically a phase of 2 pi for either one of those. So t will go to 1 when I go to the continuum limit, and I just get some weird object whose square is a projector. Okay, so now let's go from bosons to half bosons. So I told you what a half boson was, and now I want to build it from a full boson. So there's two ways to do it. I just take a regular boson, which has both X and a P, and then I can build a half boson out of it by taking linear combinations of P and X. That would be Q. And then there's a dual set of, or there's another half boson that I can build where I exchange X and P. And you can check that the Poisson brackets of the Q's coincide with what I showed you before. And the Poisson brackets of the W's are the Poisson brackets of a right mover. So if I start with a full boson, I have two half bosons, one left mover and one right mover. But the original Poisson structure of the X's and P's was non-degenerate, whereas the Poisson structure of the Q's and the W's is degenerate. So what happens is that if you start with a full boson, you can extract two half bosons, but the two half bosons, if I sum the Q's and if I sum the W's, you can see that the sum of all the P's and all the X's are in the Q's, and the sum of all the W's, you also get the sum of all the P's and all the X's. So it turns out that the Q and the W share the zero modes. So you start with a full boson, you build two half bosons, and the two half bosons share their zero modes, and what you throw away is the canonical conjugates of the zero modes. So you can basically start with full bosons, go to half bosons, but you cannot go back without introducing new variables. So once you're in the half boson world, your system stays gapless, and to make it gapped, you need to introduce some extra variables that would do the trick. Okay, that's another way to see that the theory is not trivial. But there's another projection, and this one's more interesting. I can also double the lattice. So if I start with a phase space that has X's and P's, I have two n variables. So I can go from two n variables that are X's plus P's to two n variables that are Q, and I can try to reproduce the Poisson brackets I gave you before, and you can just put the momenta on the even Q's and the differences of the nearest neighbors on the Q's, and you can check again that the P's and these kind of gradients have the correct Poisson brackets. And then what you find is that here I start with two n variables. The Poisson brackets of the Q's is degenerate. So what happens is that when we went to two n variables, and we made it degenerate, one of the variables had to be thrown away. So one of the zero modes ends up being missing in this case, because you have an odd number of variables left over. So there's only one zero mode rather than two. So if we add the extra zero mode, that means that we allow Q to the 2i plus 1 to, let's say, be a constant. And when you wrap it around the lattice to get a non-trivial result, and when you sum the x's, they cancel, but something has to give. And the statement is that X is only identified up to a period. So what you have is a notion of classical winding on a periodic lattice. So the idea is that the two zero modes, the one for even Q and the one for odd Q, one of them is like the center of mass momentum, and the other one is kind of like a classical notion of winding. So if I change momentum and winding, I have a T-duality. So it acts, I send P to the difference of the x's and the difference of the x's to the next P. So it exchanges the notion of winding and momentum. So if I do CFT, this would be T-duality. So this weird symmetry that I had is T-duality. And well, if you've seen a lot of papers about non-invertible symmetries, T-duality shows up as one of those. But I was taught that T-duality is not a symmetry. It's an equivalence of two theories. So what really is going on is if you do the same translation twice, you get a symmetry. But there's something that's T-duality, that's not a symmetry, that I need to make into a symmetry. So I need to upgrade or change the notion of what T-duality is. So first, I need to tell you something about what's allowed for C. So I'm going to assume that C is about as similar as it gets to this free boson or to the X's and P's. So that the C labels form a lattice, and that there's a unique irreducible given a set of labels. And then, as I said, I apply the transformation that I would usually call T-duality only on the maximal set of papers of labels that are mirrored, meaning that the left moving momentum and the right moving moment, or the momentum unwinding can be swapped. And then for that to happen, you require T-dual theory to have some relation between the radii of the standard theory and the T-dual theory, to have some non-trivial matching, because this is an operation that commutes with the Hamiltonian, so it also commutes with the Virasoro in the conformal field theory. The H left and the H right need to be the same. So there needs to be some relation between momentum and winding that's non-trivial, that allows momentum to be swapped with winding in some states and still get a proper state. And then the game is to extend by zero everywhere else. So the idea is that this is a projection onto an invariant sector where the original theory and the T-dual share conformal field labels of some states. So this is how you're really supposed to think about it. So the symmetry algebra, again, is D squared. Now the D comes from duality. This is actually standard in the literature. T here is translation by 2, but it's by 2 on the lattice of the Q variables, is translation by 1 on some XP lattice. And then pi is the projector onto the match labels. So again, it's the same symmetry algebra. And then one more thing, I now need to talk about modular invariance. So T-duality, as presented so far, the usual story of T-duality is that we need also a modular invariant partition function. So in this language, I have to put it by hand. I have to put in what the allowed correct C labels are. And we can actually by hand restrict ourselves to consider lattice of charges that are compatible with a free scalar. Or we can restrict it in some other way. But at this level, what I want to indicate is that you really need to know what these zero modes are doing, and all the physics is on the zero modes, and the rest kind of takes care of itself. Okay. So now let's go back to this gaplessness. The argument I gave before worked based on single valuedness of the dispersion relation. And then from the point of view of translation in the lattice of the X's and P's, what I had originally as my K space was a double cover of the regular Brillouin zone. The limit of zero quasi-momentum for left movers and right movers get mapped to different points on the double cover. And then this -1 symmetry in phase, the e to the I pi, that would show up from one to the other one, that in the square root that you would get of trying to extract which one is in the double cover at what point, since you have a double cover. This is exactly the statement that T-duality acts by -1 on right movers and leaves the left movers intact. So the 0 versus the pi is the sign choice of which one is the one where I'm applying the T-duality. Okay. Now I want to go back to the problem that Igor was indicating, is I want to build a finite Hilbert space, and I want to build a nonlinear theory that still has this symmetry. So if I have the Q variables and I translate the Q's by a finite amount, not on the lattice, but the variables themselves, translations on the Q as an algebra is a symmetry of the Poisson bracket, and then finite translations of the Q's of the target space can be gauged. So what I'm going to do is, rather than introduce a gauge field and try to couple the Q's to a gauge field, I'm just going to go straight to the gauge invariant variables of these translations, which basically are going to be some exponentials of the Q's. So instead of using the Q's as my main variables, I am now going to build new variables Ki, which are kind of built from the Q's, but they're built to be invariant under translations. And now the commutation relations in the algebra get replaced by, when I swap the order of two nearest neighbors, I get a phase, and the phase is going to pick up this commutator of the Q and the next one with an extra factor of I due to quantization. So you're going to get basically that omega is exponential to the I alpha squared. Okay. So this is a statement about algebra. I went from an algebra of the Q's to a different algebra of the K's, where the K's are built to be automatically gauge invariant under some discrete translations of the Q variables. And the Q's, remember, are targets, are to be thought of as target space. Once you have this omega, I'm going to require by hand that it's a root of unity. Okay. This is, at this point, ad hoc, except that since I wanted to do quantum computing, When omega is a root of unity, if I take an nth power of k, it will commute with all the k's and it becomes central. And this is a bosonic type operator. So if a bosonic operator is central, it becomes a C number. So I can just treat it as a C number. So what that means is that the polynomials of the k's, which is my algebra, gets truncated when I take nth powers of ki, because that is a C number. So I just replace it by a number. So what I've done this way is I went from an algebra that was infinite dimensional over the complex numbers to an algebra which in a finite lattice is finite dimensional. And therefore, if you have a finite dimensional algebra, the irreducible representations are always finite dimensional. Okay? And if you have finite dimensional representations of the algebra, that's where I put my Hilbert space, and now I can have a finite number of qubits to realize it. So again, this was a statement about choosing something for some reason that I wanted, that, you know, roots of unity are nice, but here there was a very precise reason, which was I wanted to do quantum computers. But this is interesting in its own right. It's just an excuse to do this. So let's repeat the map that I had from the p and x variables to the k variables. So the k2i would become exponential to the pi, that was the q even, and then the odd case becomes the alpha xi plus 1 minus xi. And now when you do discrete translations of pi and xi, and so long as these are compatible and with roots of unity, you basically end up with magnetic translation algebras. And then because of the gauging, and because I chose k to the n equal 1, the central element, these become n by n matrices for each one of the p, xi, and these are the usual truth matrices. So k2i becomes q, and k2i plus 1 becomes the p cross p inverse, because I have exponential to the I alpha xi plus 1 minus exponential, or times exponential to the minus I alpha xi plus 1. So the idea is that I went from this algebra to these objects that are more discrete and that look like spin objects, because now I have only n states per lattice site of. Okay. So on the periodicity, since I made them periodic, I can read their periodicity from k being single values. I can translate that all the way to the q variables. And after normalizing the zero modes correctly and everything, you can ask in CFT units, what was the radius I got? And then this was square root of 2n. Okay. This is a non-trivial computation. It's in the paper. This will come up again. So let me tell you what's going on. So if I put a spin chain Hamiltonian, it needs to be Hermitian. So I need to take the sum of ki plus ki inverse, because the ki's are unitaries, so they're not self-adjoint. So this is the simplest Hamiltonian I can write. You look at this Hamiltonian, and you have qj plus qj inverse plus this object of the p cross p inverse. The p cross p inverse is like a hopping site. The q is like a transverse magnetic field. I'm just telling you these words. These are well-known critical clock model spin chains, and then they happen to be at the self-dual point of some duality. Okay, so in the simplest case, omega equals -1. The PQ matrices of 't Hooft are just Pauli matrices, and therefore the P cross P inverse is sigma z cross sigma z, and the Q plus Q inverse is sigma x, because in this case, the Pauli matrices are self-adjoint. So the Q and the Q inverse end up being the same. So you end up getting Ising in a transverse magnetic field, and it happens to be exactly at criticality. For the next case with cube roots of unity, you get 3-state Potts model at criticality. It's also integrable. And then for n greater than or equal to 4, you get spin chains at criticality with central charge equal to 1, which is what the original Q variables would suggest if the calculation is in some sense perturbative. Okay.
David, so if you would actually couple your theory to a gauge field, you would also get extra holonomies of the gauge field. I mean, so do you have those in your model or not?
I can put them in there. Maybe if I answer next the question, you might say yes or no, depending on how you want to think about it. What I'm going to tell you is that these raw models with the Q plus Q inverse, if you just take them at face value, you get the modular invariant partition functions of some non-trivial theories. And you get the exact degeneracies for those in the continuum limit. And maybe later, the answer will be yes or no, depending on how you think about it. Okay, so basically, let me tell you what happened. The translation by one that I had originally called non-invertible symmetry persisted because we did the same on every single lattice height of the Q variables. And this was our non-invertible T-duality symmetry. So what happened is that the symmetry in the new variables is what is known as the Kramers-Vannier duality. So in all of these theories, there's Kramers-Vannier duality, and the Kramers-Vannier duality is this T-duality that I had in the Q variables. And this is also a non-invertible symmetry, and the spin chain happened to land at the self-dual point of the Kramers-Vannier duality. Okay. So with a little bit more detail, let's ask what happened to zero modes, since everything was about zero modes. So there's two classes of zero modes. There was the one of the even p's and the one of the x minus xi. So the product of the qi's is something that commutes with the Hamiltonian because this commutes with p cross p inverse. You can check that q to the n is equal to 1 because the individual q's to the nth power is equal to 1. So the symmetry of the zero modes of q gets replaced in the capital Q by a Zn symmetry. So instead of having infinite translations of little q, we now have that in the algebra that survives, I have a Zn symmetry. And there is no corresponding symmetry on the P cross P inverse because the P cross P inverse, if you telescope them, they cancel each other out. So the statement for over is that no, you don't get the Zn symmetries unless you put the windings by hand by twisting the Hamiltonian. But the idea is that there's a zero mode for the Q's, it's absent in the P's. This is important for the modular invariant properties of the system. So the Q's and the different, or the P's and the difference of the X's are treated slightly different once you end up in this, the zero modes are treated slightly different in this setup. So here's the idea. So what do I need to do? If the product of the Q's goes to the product of P cross P inverse, the only thing I need to do is to say, okay, the only way to match the labels of the zero modes is if the product of the Q's is trivial. So I need to project onto the Zn invariant state. So the duality must be projected to the trivial Q sector. Okay, so my duality symmetry is d squared is equal to translation by 1, translation by 2, projection to the Q equal 1, but this is a Zn projection, so it's a discrete group quotienting. And as I said, in the infrared long wavelength limit, t goes to 1. So d squared is equal to projection to the Q equal to 1. Okay.
And can I check my understanding of this? Oh, sorry. It looks
Yes.
like you may actually address this in the next slide. Never mind. I'll ask again if you didn't. Okay.
Okay, so here's the goal. So the projection to invariant states is a Zn orbifolding. This is what we're taught in conformal field theory. And the T-dual theory is what you also get by translation by 1. So if those two things are the same, translation by 1 and Zn orbifolding needs to be the same thing. Sorry, T-duality and Zn orbifolding needs to be the same thing. So when you orbifold a theory of radius n, you go to radius r over n. That's the way this Zn acts on the usual lattice of momentum. And then this needs to be 2 over r. And then if you replace, you find that r is equal to square root of 2n, just like I had computed trivially from my little Q variables originally. So the idea is that the symmetry is powerful in this case, the non-invertible one, because it tells you that you can, via this small calculation, determine the radius of the CFT. So if you have a radius of the CFT, you've determined the theory. Okay, when does this work? When the CFT is actually a U1 current algebra, and this makes sense. Okay, so let's try to analyze this a little bit better. Numerically, people did this, and they found that things worked, and we saw that the central charge was 1 for n greater than or equal to 4. Sorry, yes. And then there was some special cases for the 2 and 3. When people did this numerically a couple of years ago with the MRG, after a lot of work, they found the same result, that the self-dual point was square root of 2n. We also did exact diagonalization on a lattice of size 7. That was enough for us to determine the symmetry and the conformal weights. That's a story for another day. The point is that, you know, I didn't have access to all this DMRG stuff. I learned about this later. I also learned about non-invertible symmetries after we had discovered all this stuff. And then this thing that I thought was new, this kind of weird boson, turned out to be these non-invertible symmetries. Okay, so the whole point is that, you know, this was a nice way to construct these theories with some other way of deriving results for them. Now there's more details, and this is the important part. You can ask what operators are available that are both Zn invariant, and if you're perturbing around the CFT of the original Q variables. So you have dx, d bar x, that's the usual chiral current. You have vertex operators like exponential to the ikx. It turns out that the Zn symmetry ends up being embedded into little k, the vertex operators of the usual U1 theory. K must be n times larger than the minimal value for momentum, and winding one is allowed. So the statement is that the Zn invariant states are the ones that have momentum which is n times larger than usual. So since all of our theories started with Zn symmetry, right, the only allowed vertex operators are the ones that have k, which is properly quantized. And if you ask for vertex operators that carry the weight k, the minimal dimension that's allowed, or with winding, you find that the minimal dimension is n quarters, n quarters. What that means is that when n is bigger than 4, these are irrelevant, and therefore you flow to a theory that still has the U1 current. dx and d bar x is non-invariant under T-duality because it sends dx, d bar x to minus d bar x. So the marginal operator dx, d bar x is disallowed if you are at the self-dual point because the d bar x will be charged with a -1. So the non-invertible symmetry protects the radius. So the radius that I computed in the original Q variables is the one that I get in the theory. So now these are all irrelevant when n is bigger than 4, and now when n is less than 4 or less than or equal to 4, you get these n quarters, n quarters. What happens if we can now say why n4 was the barrier from passing from c less than 1 to c equal 1. When n equal to 2, 3, these operators that are in principle there, that respect the symmetries, are relevant, and therefore they make the theory flow to a theory with less central charge. So if the UV had central charge equal to 1 in the Q variables, after I consider this non-trivial Hamiltonian, the theory must flow to a theory with c less than 1. In the case n equal 4, it's marginal, they're there, and they move you away from the place where you have a U1 current algebra. So n equal to 4 is special, it's 2 copies of Ising, but there's no U1 current algebra. So what we have answered is that for n greater than or equal to 5, we know what the radius of the U1 theory is, and we have a non-trivial U1 current in the infrared. Okay, if you've seen this algebra before with a slightly different normalization, meaning you take an extra factor of n, d squared equal to n times this projection to Zn invariant projector. This is what people call the Tambaraya-Yamagami categorical symmetry for the group Cn, and it has appeared in fusion rules for chiral conformal theories for a very long time. And this is basically where non-invertible symmetries also have the name categorical symmetries, and where they showed up in various kinds before. And since Kramers-Vanier's duality is also a non-invertible symmetry, it has been around since forever, since the solution of the Ising model, basically. This is part of what the Onsager did. The symmetry changes the lattice and the dual lattice. And here we see that in the lattice sides were the p's, and on the dual lattice were the gradients of x. And then when you swap them, when you did the T-duality, you swap those two. Okay, so that's basically what I have to tell you about 1 + 1 theories. So now let's go to 2 + 1 theories. So I'm just going to add an extra dimension, keep half bosons on lattice sides, and then just add the simplest non-trivial Poisson bracket I can invent with all my nearest neighbors, and I have to choose some signs, so plus, minus, so that's translation invariant. When I do my same argument, now K is a two-dimensional vector, so the Breuerian zone is now two-dimensional. It's still true that I get a first-order differential equation for Q, so I get a single-valued omega of K, and now the crossings of zero are these lines at 45 degrees. So now you have a system with a lot of zero modes, meaning a lot of symmetries. And these are what people call gapless fractal models. So starting with these variables, translation by one will behave similarly as before. And then you get fractons. So this way of thinking about theories naturally leads to these models with weird dispersion relations that have non-trivial zeros in various forms. Okay, that's what I have to say about fractons. Almost. You can also go to the PQ variables by doing the periodic identifications, and then you take a lattice to split even and odd lattice sides. What you do is you take, for example, the face-centered 2D lattice, also known as a square lattice, but twisted by 45 degrees. Then what you do is on the even sides, you put you put Q variables, and on the odd sides, you put something that makes the Poisson brackets work with the faces. So you get this product of P cross P inverse, and you look at this, and this doesn't look like hopping at all. What it is what in condensed matter people call, I call it controlled hopping. So it's double hopping. So you have to hop on two sides at the same time, or what people also call a plaquette operator. So the Q's are electric fields and the P's are kind of like Zien holonomies. This is a plaquette. So what you get is things that are typical of discrete gauge theories in 2+1 dimensions. And you can go to higher dimensions. You can go to 3-dimensional lattices and get all kinds of weird stuff also. Okay, now just to finish off, I want to tell you a little bit about work in progress with Simon Cattrall. So staggered bosons, I told you, were similar to staggered fermions. And if you go through the list of what interesting discretization of fermions exists on lattices, one of the ones that shows up always in supersymmetry is the Kähler-Dirac fermion. So is there a version or versions of bosons that's similar to the Kähler-Dirac fermion? Okay, so what's special about Kähler-Dirac is that you can put it on any triangulation on a manifold, so you can have some very complicated non-trivial geometry. And this is where you've kind of twisted in the sense of supersymmetry, where you go from fermions to forms. So the forms, this is a little bit like discrete calculus, exterior calculus. And then when you talk about the Kähler-Dirac fermion action, the action is built from the triangulation complex exact sequence. So what's the idea? The idea is we're going to build a Poisson bracket for bosons that tries to follow this information of the exact sequences. So I'm going to basically say I have degrees of freedom on lattice sides, just like for fermions. And then instead of putting the information of the exact sequence on the kinetic term directly, I'm going to just dump it into the Poisson bracket. So what does that look like? Here's kind of the chain complex. You have a boundary of your chain complex. There's going to be some, cells of lower dimension. There's going to be some integers. So if you have these CW complexes, you can produce integers or some more general version of cells. You have a bosonic variable for each one of these lattice, or for each one of these cells. And then you put a Poisson bracket, basically associate an X variable to each one of these cells. And then you take that the Poisson bracket is this CJK, and you make it antisymmetric by hand. So that automatically brings in the dual cochain because of this antisymmetrization. So it lets you kind of build something that has the right properties. Okay, so this is my idea. You put it together, you do this non-trivial statement, and then you can build a simple Hamiltonian, which is 1/2 of xk squared. And then I'm going to say that these are my Kähler-Dirac bosons. So as I said, the Kähler-Dirac fermions have the same data for each cell. You have one Majorana variable that anticommutes to 1. So what I'm going to really do now is I'm going to take supersymmetry. I'm going to do the simplest supersymmetry I can possibly imagine, which is I just take the boson and the fermion, put them together, sum and square. Surprisingly, this very simple recipe, when you square the theta k's, you get the xk squared, so you reproduce the bosonic Hamiltonian I had before. And when you square the Hamiltonian or the supersymmetry, and you keep the term that is a bifermion, the one where it's not the same theta k squared equal to 1, but where you have the theta k's at two different places. The cost of doing that is that because the thetas are antisymmetric, you need to antisymmetrize on the x, and that means you introduce a Poisson bracket, and then the Poisson brackets of the x's produce the cell complex data, and this is exactly what the Keller-Dirac fermion Hamiltonian is. Now, once you have this form, you can start adding numbers over here, which means that you're not tied to just the triangulation of the C complex. You can couple it to gravity because you can add numbers over here. So you can add weights to different xk, theta k a little bit. So it gives you more room to add things that still preserve what you expect. Keller-Dirac fermions have a lot of zero modes associated to cohomology. So that translates into zero modes for the x's as forms on the manifold. So basically what you get here is a way to pair fermions and bosons in a nice way. And then the zero modes here are cohomology, so you kind of subbed everything up to topology again in some more traditional sense. Okay. The most general version of this is you just take some graph with coordinates at vertices, and you put some non-trivial Poisson brackets on the edges. There's choices. In a nutshell, you have pushed all the interesting physics to the edges, meaning how you assemble the Poisson bracket. And if you want to twist your Poisson brackets by symmetries, like Offer was asking, by gauging or coupling to background gauge field, you can put all of that into how you twist the Poisson brackets from 1 to some other values, so you can form non-trivial holonomies, etc., etc. Okay, so this is it. The recap is there's this weird construction that I found have bosons in 1D. It leads to gapless and symmetry protected theories if you preserve translation invariance. The result is simple to understand. So I wrote it originally as a problem in the Brilliant zone, but the real important thing is that it was governed by non-invertible symmetries. And I didn't know that what those were when I started. And to be honest, a lot of the papers on non-invertible symmetries only understood after I understood this example. So this construction explains the interesting critical theories that, can be obtained from turning these half bosons into discrete degrees of freedom. And this is basically a statement that you can even protect nonlinear Hamiltonians with these non-invertible symmetries, and you can use them to predict properties of the conformal field theory, like the radius. And then, as I showed you, this leads to interesting fracton 2+1D theories and supersymmetric models, and you can basically use these to, do a whole bunch of model building just for fun. Although I'm pretty sure that most of those models have been discovered in some place in the literature. People have done a lot of work, so I'm not going to claim that these are all new. It's just that it gives you a nice organizing principle. And remember, T-duality is this Kramers-Vanier duality. I think many of you know this already, but I'll take any questions now.
Does anybody have some questions they haven't asked yet?
I have a question.
Yes.
Yeah, so thanks for the nice talk. I'm still a little bit confused about compactness and periodicity. So the lowercase q, if I think in terms of sort of continuum chiral boson, it would be like the spatial derivative of phi, the chiral boson, right? So phi may have
space
some...
and time derivative of phi. Half of them would be space derivative, and the other half would be the time derivative. And the p's and gradients of q, gradients of x.
Okay, But if Qs are like derivatives of this of this chiral boson, which has some periodicity, I would expect that the Qs themselves don't have any particular periodicity properties, right?
The periodicity was something that I did just by hand. It was a way to build a finite dimensional algebra. And yes, one would not usually periodically identify the gradient of X and P dot directly. But the point is that from the point of view of how we were thinking about this in the lattice, there was no reason not to do it. It's very nonlinear and non-traditional, but from the point of view of just building interesting algebras, it's fairly straightforward to do. And then the statement is that statements about zero modes in one side could be converted into interesting questions about the discrete models that were obtained on the other side. And then this is the statement that Kramers-Van system duality. And yeah.
Okay, thanks.
So these spin chain models you obtained, they looked like Hamiltonian versions of the N-Potts model.
Yes, this is what people call the clock models. There's some versions of
So
these.
they're not new models, right? They're
no, these have been around since forever.
Yeah.
So Kadanov did a lot of these things in the right. So a lot of these are parafermion theories. And then what the ones I land on are the ones that have central charge equal to 1, but they're not the parafermions of Fateev and I think Samologikov. Fateev and Samologikov had some parafermions. So if you look at the full list of clock models, there is a clock model which is integrable and has central charge of the parafermions, which happens at a place of higher symmetry between these PQ variables. Those parafermions, in the continuum theory, some of them can have one of these integrable flows to theories with central charge that are lower that preserve some symmetry. So a lot of these models, the ones that have been studied the most, are not these ones directly, but these other ones that have this extra symmetry. But these are just points in the moduli space of couplings of all of these constructions. These ones that showed up here have been studied a lot by Paul Fendley. So he has a huge number of papers on these gadgets. And when I talked to him, he told me that maybe the experts know this square root of 2n, but nobody had written it in the literature in a way that was easily accessible if they know it at all. So it's one of those things that if it's something that only the experts know, and maybe even most of them don't or don't recall it, then he told me, go ahead, have fun.
Can you try to build can you try to build a non-abelian version of these theories by using non-abelian currents?
It hasn't worked so far because I cannot make the Poisson bracket to be sufficiently nice. What I can do with some of these theories is I can build Toda, I can build a Toda chain, but they treat the momenta and the gradient of X very differently. And if you swap them, what you get is e to the q and x dot kind of stuff. That's you can get various things that look similar. There's I've tried, I haven't been able to, but I'm happy with supersymmetry and coupling to a background gauge field that's discrete. I'll be happy with that. I'll take what I can get for the time being.
Do you know if there is some concrete connection between the C=1 version of your story and the modified Velan constructions for C=1 compact bosons?
I believe the answer is yes, but I haven't really studied it. So the paper of Nati and company used this Velan construction, and the story of C=1 I found later was in some papers of Clay Cordova and company, when they say that if you have this Tambara-Namagayami category, that basically that says that your theory is T-dual to an orbifold of itself.
Precisely for special values. Well, and then for special values of the radius, that gives rise to a symmetry, which is non-invertible. Yes.
Now here's the other thing that's kind of fun. We have these weird zero modes on odd-dimensional lattices. If you go to this language of these non-invertible symmetries, when the lattices have an odd number of sites in these Q variables, this is what people call this non-trivial duality defect. which is, or the gauged non-trivial duality defect, which is basically a statement that when you go around for the left movers, you're okay, and for the right movers, you got T-duality, or you got the twisting by -1. So I believe that basically this is a simple way to understand what these duality defects are. And going back to Offer's question about non-trivial boundary conditions, if you want to find the twisted version of the things where the P cross P inverse acquire a non-trivial holonomy, what you do is you do the change of variables, you insist on having a non-trivial product of Q P cross P inverse, and you can do that if in the Hamiltonian, when you go around, you put an extra phase of unity, root of unity in the Hamiltonian couplings that you can always move around, but you have to choose it at some place. So you can couple it to non-trivial boundary conditions that way. Yeah.
Right. I see. And part of the reason I asked is that there was a lot of eerie similarities between many things that you said here and stuff that appears there.
Yes.
One of them, by the way, is that there's not a nice non-abelian generalization that's known for this modified Villain technology. And the fact that you ran into some difficulties finding one here perhaps isn't a coincidence, but hopefully it is. It'd be nice to have enough.
Yeah, well, as I said, I don't have a good answer. The problem is that with the algebras, if I want the algebra like Poisson brackets, they don't admit central extensions. So it's a lot harder to kind of put it together into something that works nicely.
Yeah. I see.
Yeah, but I don't have enough of a feeling. But yes.
There's some other questions. Okay. Well, we asked a few during the talk and then a few now, so maybe this is okay. So let's thank David again for a wonderful talk.
Yes, thank you.
Thank you.
No, thank you all for the invitation. So I hope you guys have a lot of fun.
Yeah, thank you very much. Yeah, this is wonderful. Yeah, I'm very curious what if the connection between this stuff and this Villain technology can be made a little bit precise, because they seem like they're accomplishing very similar things. Arguably, yours accomplishes slightly more because you seem to be able to construct chiral bosons, whereas in this modified Villain technology, so far in the published versions that I've seen, you have nice constructions for C equals 1, but not for C equals a half. But
okay. Yes.
Yeah, interesting.
It's
very interesting. It's a very interesting. Yeah.
I would claim that since these models were known from time immemorial,
yes,
that people knew them. They just didn't know they knew them.
Very good. Very good. Okay. Well, thanks again.
Yeah. Thanks.
Yeah.
Bye.
All right. So in 2 weeks, we'll have a talk by Himanshu Raj in this collaboration. Those of you who are still here, I'll send a reminder about it.
Okay.
All right. Bye-bye. Thanks, everybody.
Bye.
Bye.
Bye, everyone. Take care.